Okay. So thank you very much for being here on the Monday morning for the second week of our GIAN course on miniaturized total analysis system. I hope you all had a great long weekend. I particularly enjoyed playing Holy on Friday. It was really good fun working with the dice as well as the water balloon. So I think it's a great celebration for someone that had never done it before. I thought that today it would be good to start off with a little bit of a recap, trying to think what we actually achieved last week. Because as mainly a chemistry, agricultural science focused audience, we've seen a lot of engineering. And we've started off looking at miniaturization of chemical analysis systems, where the main driver was to increase efficiency, with added advantages including the decreased consumption of samples and reagents, as well as the decreased consumption of power, because we don't need to pump as many liquids around in our chemical analysis system, which reduces the need for electrical power. Another great advantage of miniaturization is that everything gets smaller, which means that you can package it all up into a small box that you can either in a small suitcase or even using a handheld device can carry into the fields to do your testing close to the site of where the chemistry is taking place that you're interested to probe. The last advantage of having miniaturizing the analytical systems down to the point you can bring it to the field is that you cut out a lot of time. You don't need to transport your sample from a river to the laboratory because all the processing is automated. You don't need to do a whole range of sample preparation. So typically you get your answer about your chemistry within an hour. For small molecules, typically we can do 10 to 20 minutes. But if you want to look at some DNA, you need to have amplification. An hour is a reasonable time to get a result. Microfluidics, I've introduced you to the difference of the physics happening when we are at a sub-millimeter scale. And microfluidics is nothing more than a toolbox that enables the miniaturization of these chemical analysis systems. So we have ways that we can do the chemical analysis, the chemical assay itself smaller, but coincidentally the microfluidic timescale, the sub-millimeter, the microfluidic scale, the sub-millimeter sizing, also is the same size as that cells are growing in our bodies. So cell and systems biology can also be conducted using microfluidic system. And lastly, for those of you that are interested in the fabrication of either in organic synthesis or the fabrication of nanoparticles, microreactors are, you can do organic synthesis and the formation of nanoparticles in systems as well. Over the weekend, as I've had nothing better to do yesterday, I rearranged the lecture from Friday from applications in DNA and protein separations to have it more focused on ways of making nanomaterials and having some agricultural science applications. So it's still an applications focused lecture, but in this instance a little bit more focused on the interest of the people that are in the audience. So our toolbox has a whole range of different functions. They are to transport and meter samples and reagents, including external pumps, such as syringe pumps or pneumatically driven systems, or intrinsic pumps using either wicking, the wetting of the capillary and therefore pulling the liquids in, or using the electroosmotic flow. Because we have low Reynolds number, mixing becomes a challenge, and we looked at a couple of different ways that we can faster mix the chemical reagents. We looked at different ways of separating, so we had touched on HPLC, high performance liquid chromatography, which we will study in more detail this week, and we had an intense day on electromigration techniques for separation using either capillary electrophoresis to do the separations where we had some broadening but could achieve really high resolution. And we had separation of molecules by isotechophoresis, where we may be sacrificing a little bit on resolution, but we could concentrate the molecules from a dilute solution, could concentrate them into a very small volume, and therefore at a high concentration. And million-fold concentration factors have been demonstrated with isotechophoresis. After this separation, or a selective assay, which could be a coulometric reaction, it could be electrochemical detection, or it could be an immunochemistry or aptamer-based interaction for binding, like's done at the lateral flow assays and the COVID tests. We can detect the presence of our analyte, and that detection could be quantitative. Yes, it was there. No, it wasn't there, but we're not sure how much. Or it could be qualitative or quantitative, where we also can measure how much of our analyte was present. Good morning. Using calibration curves. So today and tomorrow we'll be focusing at a different aspect, and that is how can we actually make these devices. So we looked at why do we want to use them, where do we want to use them, what are the functionalities that we have, and for the coming 2 days we're going to look how are we able to put it all together. And the way we do that is by microfabrication. We pretty much borrow a lot of the technologies from the electronics industry. So microfabrication is best described as the foundation technology and platform for creating microsystems. It provides permanent fixed microstructures and assemblies that can allow us to conduct a wide range of functions and applications. I still have got the old slide change on. So microfabrication technologies, we all have phones in our hands. They are all made in clean rooms using microfabrication processes. Wearable sensors are increasingly around, with phones measuring or watches measuring our heart rate, measuring how many steps we've put every day. Chemical analysis, but also medical test devices get smaller and smaller. Again, measuring your physical parameters like your weight or your heart rate, as well as the chemical contamination. Do you have a certain virus or not? And then we've got applications for organ on a chip. We'll be looking at in more detail on, I think, Thursday. We'll have a lecture on how microstructures can be used to culture cells, organs, spheroids and organoids to build a little near-human system where we can test the pharmacology, the acting of drugs, and the risks associated with that. Microfabrication is mostly done in a clean room facility. And a clean room is an engineered space where there is a very, very low concentration of particulates. It is well insulated, well controlled from external factors, and actively dust and particles are always being removed. So a clean room is typically at a higher pressure than its environment. So dust and air are pushed out continuously, and the input air is filtered through a series of different filters to prevent any dust from being introduced. We'll be talking a little bit later about photolithography, the way that the microchips are made. But we use a lot of light-sensitive materials, which means that big areas of a clean room are yellow light, so that we can easily work with our materials. We don't get unintended cross-linking happening. But you can also see in this picture that everybody is dressed up to prevent the presence of a human from contaminating the environment that you're in. One of the practicalities is that if you're dressed like this and you want to ask your colleague a question, you need to know who it is. This is the only part of the face of your colleague behind safety glasses you can see. So you need to get to know your colleagues really well to put the right name to a people, because in a clean room, other than body height, everybody looks exactly the same. Everybody is dressed up in the same way, wearing overshoes, gowns, trousers, gloves, having a hood on, and in some instances also a mask to prevent any dust coming out or just skin cells dropping off. So it is a little bit of a challenge to recognize people, but at a certain point you start figuring out eyes and eyebrows. We have different classes of clean room systems, and these classes are given on how many particles are present per cubic meter. For example, class 100 clean room has got 100 particles per cubic meter. a class 10 only has got 10, and that is the kind of clean rooms that you really need to make mobile phones. For microfluidics, we're actually quite happy with the 10,000. 10,000 particles per cubic meter is still very, very little. It is a lot cleaner than our normal laboratories that we work in. And a lot of our cheaper microfabrication that I'll be talking about later, that is okay for microfluidics, actually doesn't need a clean room at all. We're going to have a little bit of a closer look on how are these devices actually made. What are the processes that we have borrowed from the MEMS industry to make these microfabricated devices. And the particular ones that we'll be going through today, in the first lecture, we'll be looking at photolithography as the basis for the standard silicon processing in the clean room. The next lecture this morning will be going towards soft lithography, which is using templates made using silicon machining or other ways, but then to cast a relatively soft polymer called PDMS on. And then this afternoon we'll be looking at injection molding and other replication techniques. And tomorrow we'll be focusing on the use of 3D printing. Professor Malik and I have been fighting for 4 days, I think, no, nearly a week. We started on Wednesday with DHL to get all the certification right, because I forgot to pack my little box with show and tell pieces. Yesterday we won the battle with DHL and we've got all the documentation that I, as a foreigner, can receive a parcel at the chemistry department whilst I'm staying on campus in a hostel. It was a very interesting challenge that I had addressed it to the chemistry department. DHL started talking that the chemistry department, people don't live there, so we needed to get a letter from the hostel. It's been all kinds of interesting numbers of paperwork, and I'm not sure if that was all necessary, but I hope by today the box will come, otherwise it's tomorrow, and it's got some show and tell pieces. The important part to realize in microfabrication, there is often not really a right and wrong. It depends on your situation, as well as the application that you've got in mind. And the approach that you pick is typically a combination of what kind of chemistry you want to do, which dictates the material that you can, but more importantly, the materials that you can't use. If you want to use a good solvent for polymer, you probably don't want to make a polymer device, you probably want to make a glass device. Whereas if you want to use hydrofluoric acid, which etches glass, you probably don't want to pick glass as a material, you're probably a lot better off with a Teflon device. Cost is your budget, and do you want to have one device or disposable, that drives how many devices you want to, what the price per device is going to be. Because if it's going to be disposable, you probably don't want your manufacturing cost to be much beyond 500 rupees. If it's a device that you're going to be using over and over again, maybe 5,000 is not a bad price. And it also very practically depends on the facilities that you've got on site. If you've got a beautiful laser cutter sitting in the School of Engineering, that may be a very convenient way for you to do rapid prototyping. Whereas if they have a high-resolution 3D printing, then you could make exactly the same structures using high-resolution 3D printing. So the facilities that you've got quick access to are an important driver as well, which very much varies from institution to institution, and explains why standardization is a great problem in microfluidics. Everybody just makes with what they've got available. So our application dictates a lot of the different areas of what we want to do. We already talked about chemical compatibility, but the analytical assay that you want to do, that puts a whole range of demands onto the microfabrication approach to choose as well. If you want to do optical detection, or you want to look at something under the microscope, transparency is going to be very important. If you want to measure the conductivity or the impedance, you probably want to have a conducting material. And we also need to be able to interface with the electronics on the outside. For separation, if we want to do liquid chromatography, we probably need to have a material that can very tightly be bonded to enclose the microchannel, because otherwise our device will pop open during operation. but conductivity doesn't really play a role. Whereas if we want to do electrophoretic separations, we want to make sure that our material is an electrical conductor, because we want our current to be flowing through our buffer to drive our separations and not around our microchannel through the device. The level of integration of our analytical processes is an interesting step as well. On Thursday, we'll be looking at functional integration. How can we integrate a filter for sample preparation, material that is suitable for the separation we want to conduct, and then have either conducting electrodes for detection or a transparent window where we can do optical detection. So integrating the different steps of the analytical workflow, each of the steps put a different demand onto the material properties that we want to get into the device. Then we have the consideration, is it going to be disposable or single use? If we want to have a reusable device, then, or we're just doing rapid prototyping to get the design right, then direct fabrication techniques are fine. But if we want to have a disposable like the COVID tests, we probably want to consider high throughput replication techniques like injection molding, because otherwise the cost is just going to be unaffordable. If we need to pay a salary for someone to make every single device, it is never going to be available for 50 or 100 rupees. So we need to then replicate it using very similar technologies to the way that we make plastic drink bottles. And the commercial potential is also important to understand where you sit in your path towards commercialization. Are you a PhD student that thinks that you can make nanomaterials using a microfluidic device and you want to test 3 or 4 different mixers? At that point, scalability of your manufacturing is not really critical. You just want to try if the design works. Whereas if you've got a full assay developed and you've got a commercial partner interested, at that point the scalability of your manufacturing approach, and if your design can actually be made by injection molding, where you can make thousands of devices for 50 to 100 rupees each, is going to be really attractive. So where you sit in the technology readiness levels, between I'm just a PhD student trying out some designs to I have my proof of concept, I've demonstrated this all works, I've got an investor, I now want to get to market, that dictates where your choice of fabrication approach as well. So during this lecture we'll start off with photolithography. And photolithography started a little bit with the history of photography, where you can see that the projection of images using lenses initially revolutionized the drawings. So here we can see, and I think it was Nicephore Nice that did this as well, but you can see that a picture of a tree on the street could be projected onto a sheet of paper and then be traced by hand. So you could make a drawing a lot easier, relying on fewer artistic skills than just looking out of the window at the tree. Oh no, that's a camera, so that was Da Vinci, that was the camera obscura. Then Nicephore Nice comes here. So this in here, we can see a man sitting with the behind his desk, and this is the very first photograph where light hit a light-sensitive substrate and changed the chemical properties wherever the light hit and didn't change the properties elsewhere, which allowed for the transfer of the light and the darkness shades into a photo. And that happened somewhere in 1826, 1827. So 200 years ago, people started making photographs. And this was done with a material that is called bitumen of Judea, which is the powdered bitumen was suspended in lavender oil. This was spread in a very thin layer on a base, and the base could be either a metal plate or a glass plate, and then it was being dried. I don't necessarily am after the history, but a lot of this processing is actually the same thing as the photolithography that we use these days for making our devices. So it's nice to see that this is actually a 200-year-old process Yes, clean rooms are fancy things, but the processing, it's not rocket science. It's very much follow the recipe. It's something people have been doing for hundreds of years. So once the thin film was being deposited onto the glass, it needed to be left for a little bit, preferably heated, to remove the lavender oil, to remove the solvent. And then there was a coating left. That would then be exposed to the light. So the camera obscura projected the light of the image of the tree outside, probably upside down onto this plate. And after that exposure, nothing was visible yet. But some of the material where the light had been hit had been cross-linked, and some of the material where the light hadn't hit hadn't cross-linked, which meant that chemically the bitumen of Judea, the material that was present in a very thin layer, had at some locations changed its chemistry and at other locations not. And that change in chemistry was facilitated by light. After development of the materials, some of the parts could be resolved and others couldn't, and the picture became to life. So this process was later on developed further to get the printed photographs, and these days we don't even do the development anymore because we just use our mobile phone. So we started off with the camera obscura, then Niepce discovered the fact that we had light-sensitive materials that we could change the chemical properties of by exposing some areas to light, not others. So the Kodak film camera came in around 1860. Then there was the Polaroid camera, where some more modern versions at the moment become available anymore, where at a party you can quickly click a photo and the print comes out directly. From 1975, the digital camera has found a way into its lives that became digital SLR cameras. The first cameras were on the phones in around 2000, and right now everybody has got the most beautiful high-resolution camera sitting on their phone, and we're snapping pictures everywhere where we go. But the process underpinning microfabrication and the processes transferring the designs onto the thin film on the wafer is exactly the same way as the Niepce used the camera obscura to transfer the image of a scene in the lab or a tree outside onto their light-sensitive material. We still use light projection to transfer a geometric pattern from a photomask to the light-sensitive material that we call a photoresist, that is deposited into a thin film on our substrate. And then we may not always use this thin film directly, but here we can see that the pattern is being transferred from the mask onto the substrate. We can see the pattern's photosensitive layer after development. Some areas are left there, some areas have been removed, which means that we now can selectively etch or remove parts that are not protected by our photo light-sensitive material anymore, and not others. So we can do some etching and selectively remove materials. The selective removal of the parts of the photoresist allow us for that etching, and the photoresist itself, it is mainly temporarily. Some parts where we talk about soft lithography, we may use the photoresist as our template, but quite typically our photo patterning is only there to do our subtractive micromachining afterwards. So we chemically etch materials away and we use our photoresist to protect. Once we've done our etching step, we dissolve our light-sensitive layer, we dissolve our photoresist, and we are left with selectively etched grooves and reservoirs. In photolithography, very much like the traditional process developed 200 years ago, we need to first dispense and deposit our light-sensitive material. And we do that with a machine that we call a spin coater. A spin coater is almost like a CD player. It's just the wafer is hauled by a vacuum chuck. It rapidly rotates around, which means that a gravitational force spreads the liquid into a very fine film, where the rate at which we speed becomes a measure for how thick the film is going to be. The faster you spin, the thinner the film becomes. Then we get the exposure to UV light, which typically happens in a mask aligner. So that's where the light exposure takes place. And then we develop where we, depending on the tone of the photoresist, we either remove the exposed areas or we remove the underexposed areas. So there's two tones, two types of photoresist. One, the UV light breaks bonds to make the exposed areas soluble. The other one that I just already talked about, the light photo crosslinks, it polymerizes and makes it insoluble. In most applications, the wafer needs to be cleaned before the photoresist is being put on. So you may want to, if you have a silicon wafer, first remove the surface-bound water, then use some HDMS to create a hydrophobic surface so that we get even wetting, and then cool back down to room temperature before depositing the photoresist. So you place the wafer. Yep.
Go to the back slide, please. We use only HMDS. That's the only material, or there?
HDMS is it is a siliconizing agent where, if you've got a silicon wafer, it can add, I think it is C18. It can add a carbon functionality, which makes the surface very hydrophobic, which means that the oil-based photoresist wets a lot more evenly. So it is a chemical that reacts with the silicon on the silicon wafer and then adds a carbon tail to it to enhance its hydrophobicity and make sure that the surface chemistry is perfect to stick the photoresist to.
Is it the only material used?
No, there's a whole way of different photoresists will have different primers. So it's the most commonly used one.
Okay.
So the wafer is then placed on the vacuum chuck, the vacuum sucks it down, you dispense the photoresist, it accelerates, and then you wait till it is kind of dry to touch before moving it into an oven without getting prints on it. The photoresist itself, it is organic light-sensitive compounds that are present in a solvent. And we've got two different types. We've got a positive photoresist where the exposed regions become more soluble, and the positive masks, which means the exposed areas, will be removed. So we'll create a dent wherever we've exposed the light. And then we've got negative photoresist where the exposed areas will harden. They will cross-link. And then a negative mask, the inverse of the picture, will be left after exposure. So here we can see with the same photo mask, with a negative photoresist, we'll be left with the exposed area as a positive feature, whereas with a positive resist, the exposed area is removed. Our resist remains where the light hasn't hit, and we create a little dent. So your mask may need to be mainly black or mainly transparent, depending on the tone of the photoresist that you decide to use. But the negative tones ones are most commonly used for microfluidics. So after the photoresist is applied to the desired thickness, there is initially a quick soft bake at a lower temperature to drive out the solvents, after which it's cooled down to room temperature, and so that it is not tacky anymore. Then we go to the mask aligner. For a single exposure, alignment is not very important, and you could just do it with a flood exposure system. But if you make complex systems where you want to have different features overlapping each other, at that point it is very important that your second exposure aligns with the features that are already on your device, and that's where the mask aligners come into play. And if you then think about the technologies used to make a phone, they are often 20-step processes where they get back to the photolithography 20 times. So, after exposure, the exposure, it's typically UV light. There's also deep UV and E-beams to get even finer resolution, but your bread and butter exposure source is UV light that travels through a light mask. The mask is black and white or black and transparent. The black blocks the light, the transparent allows it to go through, and we get our chemical reaction taking place between the resist and the light, and only the areas not protected by the mask will undergo the chemical reaction. Then we go to development, and each photoresist that you buy has got its own purpose-developed developer to go with it. Some of them, typically the positive photoresist, they develop in basic solutions, so solutions that are pH 8 or 9, whereas your negative photoresists tend to be organic solvent, like I think PECDA is one of them, but yep, so organic solvents are being more used for the negative resist. Remember, for the positive resist, it is the exposed resist that is dissolved while the unexposed remains on the wafer, whereas for the negative resist, it is exactly the other way around. And you know if it is a positive or negative photoresist because it's written on the bottle. After we've done the exposure, we hard bake, and that means that we lock the material that we've got on our wafer in place. And the hard bake typically takes place at a higher temperature than our soft bake before. And you allow the wafer to cool down to room temperature again, so you can touch and handle it. Then there's an inspection step where the pattern needs to be accurately transferred to the right location. The line width of the pattern images need to be having the correct size. And we should make sure at this stage that there's no dust particles or defects, because it's not worth processing any further. If we're all happy after inspection under the microscope that our photolithography has gone well, then it's time to go for the etching. And that is my least favorite, and at the same time really nice reagent. It is HF. HF is hydrofluoric acid.
Can you go a little slow?
Yeah, thank you. So the etching of the glass is done using hydrofluoric acid, which is a nasty chemical. If your application requires the use of glass, please check all your safety requirements if you want to do some wet etching of glass, or make sure you are in a facility where the use of hydrofluoric acid is allowed. One of the problems with hydrofluoric acid is that if it gets into your nail bed, it starts eating away your nerve system. So if you're working with HF and there would be an accidental spill and may have ended up on your hands, your nail needs to be removed, and there's a special balm to extract the HF again from your finger bed. I've not had to use it, but I had a training where they told, so every clean room using HF etching has got nail removal kits. So if you can avoid making glass devices, do so. Otherwise, make sure you follow all the precautions, because it is a very nasty chemical to be working with. Hydrofluoric acid etches isotropically, which means that it etches at the same rate in all directions. That means that if we've got a hole in our mask for etching that has a certain width, then the etching will go as much in the width as it does go into the depth. And that means that your channels always get a lot wider at the top than they are at the bottom. So here you can see we etch probably 20 micron deep, but that also means that our final feature is 20 plus 20 is 40 micron wider than originally intended. So we need to take that into account in our design phase, because we can't have our channels 20 micron apart if they become 40 micron wider during the chemical processing.
Why they are getting?
Because the etching process, it works at the same rate in all directions. So it's isotropic, which means that the HF doesn't know if it's going down or left. So at any point where the etching starts, the etching rate is the same in all directions. So we etch as quickly to the bottom as we do etch to the sides. There are some ion bombardment etching techniques as well, which are non-isotropic, which only etch in a straight line. So if you think about sandblasting, with sandblasting you have a straight beam of particles and only the particles that are hit will be removed. So that is anisotropic, you've got a clear direction. Whereas the HF etching, because it's the chemical process, it goes the same in all different directions, which means that you get under etching and your channel ends up wider. So you get under etching and your features always end up wider than your design. There are alternatives to etching glass. There is powder blasting, where with a very fine powder you can etch away, physically remove parts of the glass. And then the photoresist, because it's a polymer, it's bouncy enough to work as an etch mask as well. And there's an increased work in high power lasers to do three-dimensional patterning and structuring of glass to break it, and then it can be dissolved out. The bonding of the glass, you can get a perfect bond, but you need to have a furnace and you need to, for about overnight, so 12, 14 hours, thermocycle, go up to 650, 660 degrees, back to 600 to relieve the stresses and allow the glass to thermally fuse together, because you've got one part of your wafer that you've got etched your grooves in. You then need to put another flat wafer in top in order to create an enclosed microchannel. So you need a furnace for that. So glass is great because it's chemically inert, it's transparent, it's electrical insulating, it is strong, it doesn't deform under pressure, and it's a surface that chemists are known, is very well known to chemists. Most chemistry developed in the laboratories has been done in reagent tubes, round bottom flasks, Erlenmeyers. Chemists are used to glassware. They know how their reactions behave on glass. So that makes it very intuitive to do our chemistry in microfabricated devices, also in glass. The problem is that glass is expensive when you compare it to plastics. I just told you it's risky processing, it needs special facilities. So processing glass is expensive. It's a direct manufacturing approach, which means that you need to have a pair of hands, even though the clean rooms have some robots around. But every device needs to go through the whole manufacturing flow, from depositing the photoresist all the way to the etching and the bonding all over again. So there's no replication options. It uses hazardous chemicals. HF itself, it's nasty. Thermal bonding, there's a little bit of luck involved to get a high success rate. And glass is fragile. If you drop a glass device on the floor, it may break, whereas with a polymer device it won't. So that's the first part of today. So we talked about photolithography and glass etching. We'll take a little break now. Let's keep our fingers crossed there's tea. That seems to be a little bit random. Some days there is, sometimes there isn't. Then I'll be talking about soft lithography, which is using PDMS, very popular technique in the laboratory. And then this afternoon we'll continue on injection molding. If there's any questions, please ask, and I hope that sometime today we'll get some glass devices, but Professor Baga, he had a couple of glass devices with him, so that gives you a little bit of an idea how they look like. Thank you for listening, and let's see if there's a cup of tea.
Quickly, if I want to go through all the steps for making that, you went very hurriedly. I could see the things. First part that you were saying that coating on the wafer was done.
Yeah.
So can you repeat those in a minute?
So first you need to make sure you have got your light sensitive material on. So you pour it on or have a dispenser, and then you spin it around so that a thin film of that material sits on your wafer.
Light sensitive material.
Light sensitive material.
Yeah.
Then you put it under your light source. So you've got a lamp, a mask, and your light sensitive material.
Yeah.
The lamp shines the UV light down.
Yeah.
If your mask is transparent, it will hit the substrate. If the mask is opaque, the light can't get through.
Okay.
So some parts of your light sensitive material are being exposed, some are not.
So designing of mask is basically allowing the light
Yeah.
to fall on the specific areas.
Yeah.
Okay. So designing is basically done on the mask.
So you design the mask and you transfer the pattern from your mask to your substrate.
Okay. And thereafter, then positive or negative?
Positive or negative, so that depends if you get positive or negative features.
Okay.
You can then use that polymer film to protect during the etching. So your light sensitive material where you've removed the part here between my hands, if we put that in HF, the HF can only attack the glass that's between my fingers because the rest is still protected by the polymer.
Okay.
HF etches glass, HF doesn't etch polymer. So we'll get the action to go down and sideways. So and that goes at a rate of about 30 micrometers per second. No, per minute. Yeah, per minute.
Micrometer?
Per minute. So typically you dip it in the HF for about a minute and you've got about a 30 micron deep channel.
Okay.
So you've got a little tray, you put it in the HF solution, you have your stopwatch, you lift it out, then it needs to go through a whole washing machine to prevent contamination. Okay. The washing machine measures conductivity, and when the conductivity is low enough, the concentration of HF is low enough again so that you can handle it with a single pair of gloves, because the etching itself you do with your latex gloves and then a pair of household gloves on top, so that you've got a 2-layer protection system.
Okay, and all this process is taking place in a clean room that you specified?
Yeah, because you don't want dust to be falling on your mask during photolithography. You don't want dust to be present when you do your etching.
Quite artistic it is.
It is, well, it is all very much following protocols.
Yeah.
It's one step. So
how you design the mask? Now, this is the basic overview that you have given.
Yeah.
Designing of the mask is basically, there must be some scientific process.
Not as advanced as you'd think. A PowerPoint slide and printing an overhead transparency would already do the job.
Okay.
So you can get laser printers on overhead transparencies. Black is opaque, transparent is not. There's fancier masks, there are etched masks that you can buy, so there's really expensive masks you can get. But photographic films are, again, have transparent areas and opaque areas. But you can make, the simplest you can do is make a design in PowerPoint or any other graphical package in black and non-black. You print that onto a transparent material. There you go, there you've got your photolithography mask. Nothing special required.